Hello, welcome to the first section on our unit on electric potential. In this section, we're going to look at electric potential energy. And to begin that discussion, I'm going to remind you of material you learned in the first semester on work and gravitational potential energy. So to begin with, remember the definition of work is a force times a distance times the cosine of the angle. And to determine that angle, what you compare is the direction of the velocity to the direction of the force. Also remember that if cosine of theta equals 1, which means that theta equals 0 degrees, then you're moving with the force. And if cosine of theta equals 0, then theta is 90 degrees and you are moving perpendicular to the force. Also remember that in the case where the force in question is a conservative force, then we can take and write a potential energy for that force. So examples of conservative forces that we saw last semester were the gravitational force and the elastic force due to a spring. Forces that were not conservative were forces like friction. And the big deciding factor of whether a force is conservative or not is to think about, does its direction change as the motion of the object changes? Gravity always points downward. The object may be moving horizontal, it may be moving vertical, it may be moving at some combination. It doesn't matter. Gravity always points downward. Friction, on the other hand, changes direction as the object changes direction. If we have an incline, you might remember all the incline examples from last semester. If we have an incline, as an object moves up the incline, friction points down. And when the object comes down the incline, friction points up. It changes direction. Gravity is conservative. Therefore, we can write a gravitational potential energy, mgh, where h was the change in height of the object. One thing that I want you to think about here is pretend you're climbing a mountain. So here's my mountain, got some snow at the top, and I'm going to be climbing the mountain with my child. If we compare our heights to the ground, we're at roughly the same height here. But our gravitational potential energies are not the same. And the reason the gravitational potential energies are not the same is because we have different masses. My 5-year-old son has a much different mass than I do. So what I want to do here is something that we didn't do last semester. And what we didn't do last semester is define a quantity known as gravitational potential. The difference between gravitational potential and gravitational potential energy is gravitational potential will be the same for everyone that is at the same height. So to get there, to define a gravitational potential, I'm going to take gravitational potential energy and divide out a factor of mass, because that was what led to the difference in the gravitational potential energy for my son and I. If this is mgh and we divide by m, then gravitational potential just equals gh. Easy enough. What would a line of constant gravitational potential look like? Probably not a question you've been asked, but my guess is that you have seen a map that shows exactly this. So let's imagine a world where we have sea level, we have a mountain, and right next to the mountain there's a lovely valley. And because this is an ideal world and my artistic skills lack a little bit, we are going to assume that these are perfectly conical mountains and valleys. If I want to draw a map showing lines of constant gravitational potential for my world here, what would it look like? Well, remember, gravitational potential, I almost said energy there, just equals GH. So what I really need are lines of constant height. Okay, so my mountain is going to look like concentric circles. My valley will also look like concentric circles within my ability to draw that. And then there may be one that kind of looks like a peanut surrounding this. I feel like I've drawn a really angry alien at this point, but that's okay. Okay, so this peanut shape, this is sea level. That's my 0 meter mark. These circles over here are due to the valley, so this might be negative 20 meters, negative 40 meters, and then the little one inside would be lower still, but I'm running out of room. This is my mountain, so it's 20 meters and 40 meters, and apparently this is a mountain for an ant because these are really very not high mountains or deep valleys, but that's okay. What is this? It's a contour map. Lines of constant gravitational potential are shown on a contour map because that shows constant height. Pretty cool. Okay, well, you may be wondering how this all ties in to the electric world. Remember, this is just review and motivation and trying to give you something to put a basis for the new material into. So now let's go and think about work. So back to our definition, FD cosine theta. Well, we learned last unit that I can rewrite the electric force in terms of charge times the electric field, d cosine theta. Okay. We still have this cosine theta. So the work will be maximum when theta is 0. It'll be 0 when theta is 90. But the question we need to ask is the electric force conservative? So let me give you an example. We'll be working with this example a lot for this section. So last section, or last unit, if you will, we saw that if I have a line of positive charge and a line of negative charge, then the field in between was uniform, constant in magnitude, constant in direction. If I take another charge and launch it in here with some velocity, ooh, that's supposed to be a plus sign, it's a little hard to see, is that going to affect the direction of that electric field? Will the electric field change direction and follow that particular little charge around? And you may remember this from last unit, but no, it will not. The direction of the electric field is determined by the charges that make up those two lines of charges, and as long as this guy is small compared to those, it's not going to change. So yes, the electric force is conservative, and because of that, I can define a potential energy. So I'm going to define the electric potential energy equal to Q times E times D. Okay. Now, this D assumes motion parallel to the field. Remember that cosine theta? Same idea. Same idea with GPE equals mgh. In order to have a change in GPE, I have to change height. Here, I have to move within the field, parallel to the field, to get a change in electric potential energy. Okay, the other thing that is probably maybe not hit you yet, but will shortly, is that we have 3 E's in this equation. And all 3 mean something different. So, the first one is just the word electric for electric potential energy. Ooh, can't spell, but that's okay. We'll fix it. This E is energy. And this E is the electric field. As I said, 3 E's, 3 different meanings. There they are. So how do you keep them straight? Well, typically, this is a unit. When we refer to the electric potential energy, we always write EPE. Okay. So typically, we're not going to have to worry about that so much. But what we might have to worry about is just an E alone for energy versus an E for electric field. I will always try to indicate which one mine is. It may be a verbal indication, but I will try to do that. If you get confused, make up a notation that works for you. So maybe you like, oh, that was not a very good curly E. I'm going to try again. Maybe you like curly E's, or even just like E's like this and E's like that. Or maybe you like to put a little flag on your E. Anything to keep things from being confusing. Make it work for yourself. The other thing that may have you scared is the fact that we now have 2 EPEs. We have the electric potential energy introduced here, and we have the elastic potential energy from last semester. And while we could imagine a charged object hitting a spring and interacting with it, and therefore changes in electric potential energy happening at the same time as changes in elastic potential energy, I'm just going to not go there. I won't give you a problem that involves a spring that also involves electric potential energy. We will not have to worry about these 2 things simultaneously. Okay, so back to the topic at hand. Electric potential energy is charge times the external electric field times the distance we move within that field. And that depends on the size of the charge that we put in there. But oftentimes, as we saw with electric force and electric field, what we have is a set of charges that set up the field. And then what we want to do is be able to change things out quickly. So I'm going to make a definition. Much like I defined gravitational potential, I'm going to define electric potential here. So EP is going to equal electric potential energy with that factor of charge removed. So remember that was QED, divide by Q. So this just equals ED. And now, since I've called attention to all the E's and how confusing it can be, and now I have an EP and an ED, and oh my goodness. Yeah, we agreed with you at this point. So we're going to give a new name to the electric potential. So kill this. We're going to call it voltage. And kill that. Just set it equal to V. Voltage is essentially electric potential energy. That's all it is. Okay? There it is. So now we have voltage, we have electric potential energy. Let's go back and think about conservation of energy again. So we're going to revisit the idea of conservation of energy. So I'm going to define a positive line of charge, a negative line of charge. I'm going to make a line. Let's get rid of that and try again. Make a line halfway in between. So this is a distance D and this is a distance D. And on this line, I'm going to set a positive charge and a negative charge. Okay. Well, we saw that the electric field will point out of the positive charge and into the negative charge. We also saw last unit that the positive charge will start to move with the field, whereas the negative charge will move in the opposite direction once released from rest. Okay, before I go too much further, I want to make a couple of definitions, if you will. I'm going to let the positive charge have a charge of Q and a mass of M positive. And I'm going to have the negative charge have a charge of negative Q and a mass of M negative. Okay. It seems a little weird. Why would I want to do that? If the positive charge were a proton and the negative charge were an electron, then this is exactly the situation you would have. The charges would be the same side. Ooh, let me try saying that again. The charges would be the same size, but have opposite signs, and the masses would be different. And it would be the case that the mass of the positive charge, the proton, would be bigger than the mass of the negative charge, the electron. So I'm going to keep with that as well. The other thing I'm going to do here is I'm going to define my electric potentials. Okay. Now remember, with potential energy, I am free to put the zero wherever I want it. I'm going to put the zero right here where it starts. Might as well. Positive potential there, and negative potential here at the negative plate. You may be wondering why I did that. Well, let's flash back to gravitational potential energy for just a minute again. And if I think about a mass starting in the air, typically I define this as my zero, and then this would be some mgh up here. And if I release this mass from rest, it falls downward, which means it moves towards lower gravitational potential energy. By making this setup like this, I have guaranteed that my charges, when released from rest, will do exactly the same thing. They will move to lower potential energy. Both of them. So now let's prove that. Let's start with the positive charge. Okay. So the positive charge, we've already said, will move to the right because it moves with the electric field or is attracted to the negative line of charge, however you want to think about it. And now I'm going to think about its change in electric potential energy is going to be, hold on one second. V equals ED. So remember, electric potential energy was QED. So now I can write electric potential energy in terms of the voltage as QV. And that's what I want to do here. Okay, aside complete. Coming back here, change in electric potential energy will be the final electric potential energy minus the initial electric potential energy. Final is going to be the charge, which is Q, times the voltage, which is negative V, minus the charge of Q times the initial voltage, which I've set up very carefully as 0. And this is negative QV. The change in electric potential energy is negative, meaning it has moved to a lower energy state. Okay. If we think about the negative charge now, its change in electric potential energy, same definition, is going to be the final energy minus the initial energy. The final energy is its charge, which I've defined as negative Q, times its final potential, which is V, minus, I lost a minus sign, so let's put it back in, minus negative Q times 0. And that also equals negative QV. So it also has moved to a lower energy state, even though it's moving in the opposite direction. Okay. So now let's think about what implications this has for the kinetic energy and the velocities and things like that. So I'm going to use conservation of energy. So this E initial equals E final. Remember, these E's, both of them here, are energy. Okay. Initial energy will be the initial kinetic plus the initial elastic potential energy. And that's going to equal the final kinetic plus the final elastic potential energy. Okay, now I'm going to rearrange this a little bit. And what I want to do is move this EPE to that side and this KE to this side. So KE initial minus KE final equals EPE final minus EPE initial. Okay. For both of our charges, the positive and the negative, we know what this quantity is. This is the change in electric potential energy that I found on the previous slide. And for both of them, it was minus QV, where this Q now, if you think about it, has to be absolute valued because I've already put the minus sign in for the charge on the negative charge when I did the calculation. Hope that makes sense. Kinetic energy initial will be 1/2 m V initial squared plus, that's plus, should be a minus, so let's get rid of it, minus 1/2 m V final squared. I said it several times. I don't know if I wrote it, but V initial equals 0 because we're releasing from rest. So this is going to be 1/2 m V, I'm rewriting and I'm not plugging in, so let's try again. 1/2 m times 0 squared minus 1/2 m V final squared, which means V final squared equals 2 times the absolute value of Q times V divided by M. And now you're probably looking at this and going, oh, I have two V's, and those two V's are not the same. This V, remember, is a speed, or V for velocity. That one is a voltage. Okay. To me, the thing that indicates one versus the other is the fact that there's a subscript, and that's enough to me to think about V final. But just like with the E's, if you want to put a little tail or maybe two tails or something to distinguish your letters one from the other, that is perfectly fine. Whatever works. Okay, now back to our example. Remember that we had the situation that the positive mass was bigger than the negative mass. And the repercussion of that is that the final velocity for the positive mass will be smaller than the final velocity for the negative mass. Okay, so the larger mass will be moving slower when it reaches its line of charge. It will also take longer to get there. Okay. Blank slide. So which way will it go? A negative charge is initially at rest in an electric field. Will it move to a region of higher potential or lower potential? It is going to go towards higher potential. Okay. It has to go to higher potential in order to move to a region of lower potential energy. Would a positive charge go the same way? No, it will go opposite. Okay. How does each charge's potential energy change? Both move toward lower potential energy. This concludes this section of this unit. In the next section, we're going to focus in on the electric potential due to a point charge.